Okay, so the first speaker in this session is Professor Daniel Rohrlich from Ben-Gurion University. Daniel wrote extensively on fundamental aspects and effects of quantum mechanics. For example, in the famous PR boxes, the R is for Rohrlich, where the P and the P is for Popescu. The Popescu-Rohrlich boxes are part of an attempt to discover features that uniquely characterize quantum theory relative to other possible theories. The foundations of quantum mechanics is the topic of Daniel's 2005 book, written in collaboration with Yakira Aharonov, Quantum Paradoxes, Guide for the Perplexed. Recently, he wrote, for example, on protective measurements, on the PBR argument, on problems concerning the classical limit, and on quantum Cheshire cats in the context of the post-selection approach to quantum mechanics. For me, as a philosopher, Daniel is a constant source of inspiration in always reminding of the need to keep contact with experiments. Whenever I use the phrase "in principle," I see in front of me his suspicion of this notion. Today, Daniel will speak about retrocausality as an axiom. Please.
Thank you very much, Orly, and thank you to all who have come. I'm going to give a lecture, I guess, but I'm also going to tell a story, because this is a story about a certain line of research. And it started in a certain place, which was dissatisfaction with quantum mechanics and especially quantum non-locality. And it got to a certain point, and then only about a year or two ago, I started to think about time and read about what others have said about time and retrocausality. So this is relatively new, and the first half of the talk won't reflect, won't be about retrocausality, first half or third or so, but we'll get to it. So I'm going to start with a quote from Einstein. Everybody knows the spooky actions at a distance. I think it's worth hearing the whole quote. I admit, Einstein's writing to Max Born, who of course produced the Born rule for interpreting quantum mechanics. I admit, of course, there's a considerable amount of validity in the statistical approach, which you were the first to recognize clearly as necessary, given the framework of the existing formalism. I cannot seriously believe in it, because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky actions at a distance. What Einstein is, the principle that Einstein is invoking here, he doesn't say it by name or by definition really, but it's the principle of locality. No action at a distance. Things should influence their surroundings in time and space, not things that are far away. But not everyone agreed with Einstein. Not everyone was troubled with Einstein's with what troubled Einstein so much. And here's an interesting quote from Pauli, again writing to Max Born, also writing to Max Born. As Otto Stern said recently, one should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same, than about the ancient question of how many angels are able to sit on the point of a needle. But it seems to me that Einstein's questions are ultimately always of this kind. So here we have two very starkly opposing points of view by two physicists who have been called the two greatest physicists of the 20th century. Okay, so in order to focus on what's wrong here, I assume that all of you know quantum mechanics, but I'm going to do something even simpler than quantum mechanics. I'm going to do a parody of quantum mechanics. So the parody of quantum mechanics involves two intrepid experimental physicists, Alice and Bob. They each have their own laboratory, and they're going to make measurements on photons which are emitted in pairs from some source. One photon goes to Alice, one goes to Bob, and they get lots and lots of these, so lots of these pairs. They do the measurements on each pair And this is really a space-time diagram. So in some time, the photons emerge back-to-back from this little thing here, and then Alice and Bob make their measurements at a later time, and their measurements are space-like separated. So there's no way for Alice and Bob to communicate directly, or no way for their measurements to communicate. Okay. So here's the space-time coordinates, the axes, to make it clear. And the parody of quantum mechanics is that when Alice measures A, she can get 1 or minus 1. The result of all of these measurements is 1 or minus 1. So she can get A 1 or A equal to minus 1. If she measures A prime, she can get A equal to 1 or A equal to minus 1. But if she measures A, Bob, who is also going to get 1 or minus 1, will find that B is equal to B prime, except he doesn't find that because he's not allowed to measure both B and B prime. He can only measure B or B prime. If Alice measures A, B is equal to B prime, but Bob doesn't know that. If Alice measures A prime, then B is equal to minus B prime. But again, Bob doesn't know that. In fact, Bob's chances of getting B or B prime, sorry. If Bob measures B, he gets 1 or minus 1 with equal probability. If he measures B prime, he gets 1 or minus 1 with equal probability. The same is true for Alice. In fact, this is completely symmetric, but I chose to make it asymmetric and talk about Alice and how she could influence Bob. Well, she can't influence Bob. There's nothing that Bob can measure at the moment that would tell him what Alice chose to measure. But if only he could get around this restriction, then it would be a cinch. Alice would choose what to measure, and immediately Bob would know if B equals B prime, Alice measured A, and if B equals minus B prime, Alice measured B prime, and that's one bit of information, and it would be transmitted instantaneously. It would be like doing this to Einstein's demand of locality. Now, as I say, this is a parody of quantum mechanics. Quantum mechanics actually is quite a bit like this. In the offensive violation of what we expect from locality, it's exactly like this. Just the statistics are more complicated in quantum mechanics, so you have to work harder to find the same result. In particular, quantum mechanics has a rule of complementarity which prevents Bob or Alice from measuring both the B and the B prime or the A or A prime simultaneously. But that's really not a thing that a decent theory should have. I mean, to invite a violation of locality and then cover it up by some rule that doesn't have any intrinsic relation with the rest of the theory is a fig leaf. That's a fig leaf, and it's only there to prevent us from seeing nature's pudenda. So Bell clearly identifies himself with Einstein's point of view when he writes, well, it was as an interview with Jeremy Bernstein. For me, it's so reasonable to assume that the photons in these experiments carry with them programs which have been correlated in advance, telling them how to behave. This is so rational that I think that when Einstein saw that, and the others, like Pauli, refused to see it, he was the rational man. The other people, although history has justified them, were burying their heads in the sand. Now, I think it's very interesting, this phrase, although history has justified them. What did Bell mean? I think, well, what he obviously meant, at least, was that history has justified quantum mechanics. We have these non-local quantum correlations. We're stuck with them. And it's very interesting from a historical point of view that the person who discovered and extracted and teased out the non-locality of quantum correlations was somebody who really didn't want to see them at all. This was a big disappointment for Bell. But beyond the fact that history has demonstrated quantum mechanics, is this a cry of despair? And to answer that question, I'd like to go back several centuries and pick an example of another letter, this time Newton writing to Bentley, and he's talking about his own law of gravitation, law of universal gravitation, saying that, the gravitational force between two bodies is equal to their product of their masses divided by the distance between them squared, and then there's a constant. Okay? And this is his own theory, and people loved it and did all sorts of wonderful things with him. But he himself is not at all convinced that this makes sense. That's remarkable. He said the gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance, through a vacuum, without the mediation of anything else, by and through which their action or force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters any competent faculty of thinking can ever fall into it. So, what is Newton protesting? Action at a distance. Was he right? Well, it took more than 2 centuries, but Einstein proved that Newton's intuition was correct. There is no action at a distance in gravity. Gravity is a field, propagates locally at the speed of light. So, what I want to inject here is a note of optimism that this locality that we seem to be stuck with, right? Every one of us has some spot on his wall in his study or office where there's a little bit of red from banging our heads against the wall, right? Because we can't stand, or maybe they're not. Maybe they're people who don't care about it at all. But some of us at least are very upset, and as Merwin said, anybody who's not worried about Bell's theorem must have rocks in his head. About which more could be said, but I'll leave it at that. So I'm trying to inject some optimism that maybe on the short scale of things, it really looks like we're stuck with this awful non-locality, but maybe in the long run, we've overlooked something. Now, I'll leave that aside because what I'm talking about first is the beginning of the story, which has to do with non-locality. Retrocausality enters a bit later. In particular, the first part of the talk has to do with deriving quantum mechanics from a different set of axioms, and it's only at the end that we return and consider retrocausality as a possible axiom. So we know, we're all familiar with the axioms of quantum mechanics and how strange they are, that we have observables which are linear Hermitian operators, and that observables correspond, and that states correspond to vectors in a Hilbert space, and okay, it's awful, really. I mean, it's not clear whether this is talking about physics or about useful mathematics. You want to study quantum mechanics? Here's some take a course in linear algebra. That's, okay? It's hard to understand where all this is fitting together. And as my mentor, Yakir Aharonov, commented a long time ago, it's like deriving special relativity from the wrong axioms. Maybe we wouldn't understand special relativity the way we do if we didn't have the right axioms. Maybe we started from the axioms that fast objects contract in the direction of their motion, moving clocks slow down. What kind of axioms are those? At least they're about physics. But why? What kind of a basis is that for a theory? Okay. And if case you think that this is exaggerated, let's look at Poincaré, who still in 1909 gave a series of lectures on La Mécanique Nouvelle. And when he got to relativity, he said one needs to make still a third hypothesis, which is much more surprising, much more difficult to accept, one which is of much hindrance to what we are currently used to. A body in translational motion suffers a deformation in the direction in which it is displaced. Okay, that really bothered Poincaré. It doesn't bother us. Why doesn't it bother? It's true, but it doesn't bother us. Why? Because we realize that it's a consequence of the first two axioms of, and it's not something we have to assume. And for Poincaré, still in 1999, he thought it was something an axiom we have to add. So this is a comparison of the axioms. This is a continuation of Yakir Aharonov's comment. Let's look at the axioms of special relativity. We have one which is inertial frames, a clear physical statement of a fundamental symmetry, right? All inertial frames are equivalent. And we have the constancy of the speed of light. That's a statement about a fundamental physical constant. Those two things have clear physical meaning, and from them we can derive essentially all of relativistic kinematics, essentially all of relativity, special relativity, except make some ad hoc assumption about masses. But the secret of this beautiful logical structure is that two things that we would think contradict each other, they don't contradict each other. You think if the speed of light, if inertial frames are equivalent, then I just hop on a train and I'll change the speed of light because I'm chasing the speed of light. It has to be slower. Anybody in Newton's time would have said those are a contradiction, except maybe Newton. I don't know, but they don't. And Einstein found the only possible way to reconcile those two axioms, and that was all he needed. So what Aharonov and Shimoni independently suggested, well, there's a structure like that in quantum mechanics as well. There's quantum non-locality, which seems to be a given, but on the other hand, we cannot use any quantum correlations to send a signal faster than light. And you'd think that's a contradiction, because if there's non-locality, means action at distance, well, what's to stop you from influencing something far away and getting a message across? And then you understand, well, there must be some fundamental randomness in this theory, because otherwise a deterministic action at a distance would be too much. So maybe that's a basis for a new starting point for deriving quantum mechanics. Well, this parody of quantum mechanics that I gave you earlier was actually my attempt with Sandu Popescu to test whether we could derive quantum correlations from these two axioms. We'll get something which is non-signaling, and it's non-signaling because Alice and Bob individually will get 50% 1, 50% minus 1, no matter what they measure and no matter what Alice measures. So it's non-signaling, but it's non-local. And that's a counterexample to our conjecture, or to Yakir's and Abner's conjecture, that with those two axioms we could derive quantum mechanics, or at least a part of quantum mechanics. And it was very frustrating, because you think that's a really nice conjecture, and the first thing we try it on fails. So for me, the PR box was a big failure. But now I'm going to revisit this problem. Actually, I started to revisit this problem 2 or 3 years ago. And I said, let's try to be a little bit more discriminating. We're not comparing apples and oranges. We're comparing quantum mechanics, which is a serial Nobel Prize winner, with some ad hoc super-duper correlations that we invented. That's not the way to do it. Quantum mechanics is subject to constraints. It has, in particular, a classical limit. Let's see whether any so-called competitor of quantum mechanics can do the same. In other words, we shouldn't just talk about a PR box correlation. We should say, if we impose on the PR box that it should have a classical limit, then let's see whether it can still survive and outdo quantum mechanics, outdo quantum correlations. So that's a kind of, this demand of a classical limit is a kind of minimal demand, a boundary condition on any kind of correlations that should compete with quantum mechanics. And let's see what happens when we impose this. Well, we're now going to assume that Alice and Bob can share as many of these boxes as they want. They have n boxes, n can be anything. And so they can also define macroscopic observables, which is you take lots and lots of B's, or say Bob measures lots and lots of B's and takes the average value instead of, it's not going to be 1 or minus 1 anymore. It's going to be some average. And if there's also a B prime, which you could take the average of. And now, that fig leaf must drop. Because in the classical limit, there is no complementarity. There are no non-commuting observables. Bob should be able to measure B, capital B, and capital B prime to some accuracy. Okay, there's some uncertainty with the measurement, but that uncertainty should get smaller as n gets larger. And in any case, he should be able to measure these two things with some amount of accuracy. We can't tell him that the moment he measures big B, he can't know anything about big B prime. That would be like saying that he's still in the quantum world. No, he's not. He's in the classical world. Now, Alice can simply generate values by choosing that over all these n pairs of that go out to Bob, and she keeps one, Bob gets one. Out of all of these, she measures just, say, A. That means that B and B prime will be equal. Big B and big B prime will be equal because she measured A for all of them, and that means little a for all of them, and that means that they all have to be the same. Whereas if she measures B prime consistently, then big B is going to be the opposite of big B prime. Again, Bob has some inherent uncertainty in his measurement as well. And in particular, B and B prime, each of these different values of B1, B2, and so on, they're all independent of each other, which means that one of them could be 1, the next one could be -1. They average out to 0. So he's going to have a very small quantity to measure. It's going to be of the order of 1 over square root of n, and we're pushing n large, and then this difference is going to be small. But in fact, it's not a problem at all. The reason is that all it takes is a lot of money and strong will in order to wait around for just a chance occurrence that all the BI's are the same. So it'll happen with frequency 2 to the minus n. Well, that costs a lot of money. It requires a lot of determination. It's not my money, it's not your money, and it's not our experiments. Let Bob and Alice do it. Think of centrifuges, right, to get out the uranium. If there's a will, there's a way, right? And that means that eventually, after 2 to the n experiments, Alice will be able to Bob will be able to see clearly what Alice's intention is. It may be enormous trouble and expense to get one bit of information across, but that one bit of superluminal communication is all. I mean, relativity doesn't stand or fall on whether superluminal signaling is cheap and convenient. Any of it is the end of the relativity. So in particular, for example, if Bob finds that B is equal to 1 for all of his measurements, then he will also find that B prime is equal to 1, and he will never find that B prime is equal to -1. These are correlations that tell him what Alice is choosing to measure. So this is a very non-technical explanation, and I would have to get into technicalities if I wanted to take it further. But the point is that just this minor additional axiom of a classical limit allows us to eliminate the PR box, and in fact, to eliminate all non-local correlations that are stronger than quantum correlations. So this is very nice. This would give us a part of quantum mechanics, namely, which is called Cyrilson's bound, the maximum violation of Bell's inequality. We can prove that bound, which Cyrilson proved using quantum mechanics, with just those 3 axioms. That's all it takes. So that's a nice starting point. We get a certain amount of quantum mechanics for free, well, not for free, but for 3 axioms that make sense. And in fact, if you go through the proof, it also even tells you that there's a Hilbert space there. The way that the correlations have to accumulate in order to be non-local and yet not break Cyrilson's bound hints very strongly at a Hilbert space. Okay. Now, we've already seen Poincaré, but I want to go back to him because there's something is very rotten in what I did up to now. Namely, Poincaré made the Fitzgerald contraction an axiom, and therefore he suffered. Is it any better in my case? I made non-locality an axiom. That's what we're supposed to get rid of. When I made it into an axiom, that's not going to make life better. So this is a warning. I mean, this example is a two-edged sword. And so I became very interested when I started to read about retrocausality, especially after I met Hugh Price and corresponded with him. But even before, when I'd already purchased his book. And retrocausality offers itself as an alternative to non-locality. And it's an alternative that might even not only get us out of the mud, but might even be palatable. We might be able to eat this with a fork and a knife, because what Price is talking about is a fundamental symmetry also. It's a fundamental symmetry at the microphysical level, right? In microphysical level, there's almost nothing that we know of that violates time reversal symmetry. It's only the macrophysical level, in which we have people and desks and trees and so on, that we know that there seems to be an error of time. But if we could exploit the microphysical error of time to give us what we think are non-local correlations, that would be very heartening, very encouraging. And I want to soften you up to this idea of retrocausality by giving you an example which I claim shows that retrocausality is inherent to quantum mechanics. Namely, and the example is a little bit strange because Price would look at this example very differently. But I'm saying, let's take the starting point that there's no retrocausality in quantum mechanics. Let's interpret everything in the usual way. There's non-locality, but there's no retrocausality. Even so, we're going to end up seeing that retrocausality. Okay, what's the example? Well, we'll take Alice and Bob, we'll introduce them to Jim, and we're going to manufacture for the three of them lots and lots of spin-and-a-half particles, triplets of spin-and-a-half particles in what's called the GHZ state for Greenberger, Horn, and Seilinger, right. Which are entangled states. So they're entangled states shared by these three people, Alice, Bob, and Jim. But even though the starting point is totally symmetric among the three of them, we're going to give Jim a special status. We're going to call him the jammer. And he is going to decide, according to his own free will entirely, whether the remaining particles held by Alice and Bob are going to be in an entangled state or a product state. And how does he do that? Well, it's very simple. If Jim measures sigma z, then what's left to Alice and Bob is clearly a product state. It's a mixture of product states of up, and down, and down. It's a mixture, but those are both product states in the mixture. Whereas if he measures, say, sigma x, he again leaves their state, the state of the remaining particles in a product state, in a mixture. But this mixture is a mixture of entangled states, which I think I left a plus out of here somewhere. Okay, so one of these should be, let's say this is a plus. It's a mixture of entangled states where both particles have spin x in the same direction or in the opposite direction. All right. Now that's it. He's determined whether their spins are entangled or not. Now there are two different scenarios. There are many scenarios, but let's look at two scenarios about how he might do this. It could be that Jim is in the past light cone, or that Alice and Bob's measurements, which are denoted by A and B, are in the future light cone of Jim's measurement. Jim decides sometime in the past whether he wants those remaining pairs resting in the hands of Alice and Bob to be entangled or not, and he simply measures one or the other, and Alice and Bob, through their measurements, because they're doing this lots of time, will discover nothing, actually, because all they will do is they will measure the spin in some directions. We'll say don't measure the spin in the z direction, but any other direction you want, measure those. And they will not know, still they will not know whether their particles are entangled or not, because they need to know the result of each of Jim's measurements in order to say whether their particles are entangled at all, and if they're entangled, whether they're in the plus state or the minus state, the state with a relative minus or the state with a relative plus. But if Jim tells them the results, then they can bin their answers and say, all of these results have to do with the minus state, and all of these results have to do with the plus state, and we can, on each state, individually verify that those states are indeed entangled. So entanglement is an objective property. Either those correlations violate Bell's inequality or they don't violate Bell's inequality. But what's interesting here is that J, which is Jim's measurements event, could be could have Alice and Bob in his past light cone, in its past light cone. There's no reason why Jim has to decide so early what he's going to measure. Alice and Bob could do their usual measurements in all kinds of directions for all different triplets or pairs. And Jim, when it comes around to it, says, I'd like those pairs to be entangled. Today, maybe it's April Fool's Day, let's make it non-entangled. Let's make them product states. He can decide right up to the last moment, and everything that Alice and Bob measured is consistent with whatever he chooses. It's only when he tells them what he got that they can do the sorting out and actually verify that he chose, that their states are entangled or not according to his choice. So this is retrocausality. Run away from it, it will still come to you. So this is what I've just said. It's causal. Jim's choice of what to measure is retrocausal. Its influence is retrocausal, but it's also causal in the sense that he cannot signal. Alice and Bob could be someplace else entirely, but he still can't signal to them superluminally, because the only way that Alice and Bob can find out whether their states are entangled or not, whether their particles are their pairs are entangled or not, is when they get the information from Jim, which they could have gotten. If he sends them results of his measurements, he could send them any single he wants, and it'll be totally causal. So this combines three things: retrocausality, no signaling at all, in fact, and free will. There's no reason to doubt that any of these characters are limited in their exercise of free will. So now let's go to Bell's inequality and look at A, which is kind of a reversed EPR experiment. Namely, again, it's a space-time diagram. Let's suppose that two photons, for reasons best known to themselves, are converging onto the area where Alice and Bob have their laboratories. And as one photon passes through Alice's lab, she measures its polarization, or if it spins, then let's say she measures the total spin state along some axis. And Bob does the same for the particle coming to his. And eventually they converge where Claire, in her laboratory, can measure whatever she wants. But she's going to measure either an operator which has product states or an operator which has entangled states as the eigenvalues. So if she chooses to measure product states, the whole thing is not very interesting. But if she chooses to measure, say, an operator which has the Bell states, which are all entangled, then again she'll get whatever she gets, and she'll get Alice's and Bob's results eventually, and she can put everything together and bin the results of her measurements so she knows which of the four entangled states she's doing it, and she will get the correlations which so famously violate Bell's inequality. But there's nothing slightly non-local happening here. Everything is local. Alice and Bob make their measurements. The two particles converge to a single point where they produce some entangled state, and it's perfectly local. But the correlations are still the correlations which violate Bell's inequality, because whether we take the initial state to be psi A, psi prime B, which are the two results of two states after Alice and Bob measure, and project them on B, on one of the Bell states, or do it in the opposite order, it's the same correlations. So that hints very strongly that maybe the second diagram, in which Alice, Bob, and Claire really do test for violations of Bell inequality, could be better understood as as retrocausal, namely, just as in A, Alice and Bob somehow the results propagate backwards in time to C, where they'll meet their fate of being either entangled in one state or another, or not entangled at all. But it's all local. It's retrocausal. It's happening backwards in time, but it's happening locally along that line that connects, those lines that connect A and B with C. And that's a very attractive idea. Can we make sense of it? Well, already in 1964, Aharonov, Bergman, and Leibowitz pointed out that if you don't insert an arrow of time into quantum mechanics by hand, then you can do quantum mechanics perfectly well without an arrow of time. Now, what do we do to insert by hand an arrow of time? We talk about collapse. We talk about the Born rule and so on. But that's, of course, inserting an arrow of time by hand because we're starting with a certain state that we know and we're ending up with a state which we don't know. Suppose we start with a state that we know, we do all kinds of measurements, and then we end with another state, and we're going to demand that that state be only a particular state that we know, something that we're experiencing. So we're starting with psi in, and we're ending with psi fin, and we're going to look at various results of measurements that were made intermediately. And we'll find that the results are invariant under time evolution. In fact, you can see it directly from the formula, because although in the first line I've written the evolution as starting from a certain t in to a time t intermediate, or t of the measurement of m, and then from then on to the final, you can simply reverse the second evolution, have it, instead of having it apply to m, its adjoint applies to psi fin. So it's simply, these two unitary operators are evolving the endpoints in the time to the intermediate place. And there's no arrow of time here at all. Which leaves open the possibility that the arrow of time, which we certainly see, is not quantum in its nature. It's coming from someplace, certainly. Maybe from the fact that we started in a universe which had very low entropy. But that's a macroscopic physical idea, and Hugh Price and his colleagues are right in saying there's nothing in quantum mechanics that necessarily violates time reversal invariance, or time reversal symmetry, rather. So now if I go back to the PR box and define and say it's not a non-local box at all, it's a retrocausal box. Why? Alice and Bob make their choices of what to measure. Alice measures A or A prime, B measures B or B prime. Those results propagate backwards in time and come to some PR box which generates the answers 1, 1, or minus 1, minus 1 with equal probability for the first three categories of measurements, AB prime, and A prime B. And but if it's A prime, B prime, then that box generates 1, minus 1, or minus 1, 1 with equal probability. That will give you exactly the correlations of the PR box. And now we're back to the same ballgame before. That PR box, which now is a retrocausal box instead of a non-local box, but for all other intents and purposes is exactly the same box, does not have a classical limit which respects relativistic causality. And therefore we can eliminate it, and along with that we can expect, I haven't done this explicitly, but it follows almost automatically, we can expect to get rid of all stronger than quantum correlations, and we now have the chance of deriving quantum mechanics from three axioms which are relativistic causality, local retrocausality, and the existence of a classical limit. Which to me sounds like a very more beautiful basis for quantum mechanics than what we started out with. Now, I don't know. Okay. Bell had something else to say, which I think is very nice. I mean, Bernstein asked Bell, well, what about this, about Bohm's pilot wave theory with hidden variables, and which Bell fell in love with at some point, and he said, but then Einstein I think Wheeler presented this idea to Einstein, and Einstein said, "Oh, it seems a little bit too facile for me." And this is Bell explaining Einstein's. I think Einstein thought that Bohm's model was too glib, too simple. I think he was looking for a much more profound rediscovery of quantum phenomena. The idea that you could just add a few variables in the whole thing, namely quantum mechanics, would remain unchanged apart from the interpretation, which is a kind of trivial addition to ordinary quantum mechanics, must have been a disappointment to him. I can understand that, to see that all you need to do is to make a hidden variable theory. I'm sure that Einstein and most other people would have liked to see some big principle emerging, like the principle of relativity or the principle of conservation of energy. A little anecdote before I end, because this is really the end. I was in a conference in India, and somebody got up. It was about foundations of quantum mechanics, quantum information theory, and non-locality, of course. And somebody got up and said, "I think that there's a way around. I think that Bell's conclusion was not correct. There's a straightforward way to avoid Bell's conclusion." And I somehow could feel the tensions in the audience rise. Like if it had been some other circumstance, not in a distinguished lecture hall with organized talks, but in, say, in the field, I think we could have really gotten up and tied him to a post and stoned him. We'd all thrown stones at this guy. And I was wondering why this animosity. And I think that it's understandable. Namely, all of us who responded that way, at least, have, as I said, left these red marks on the walls. We've all suffered through Bell's theorem, and the last thing we want is somebody to say, "Oh, I have this gimmick for avoiding Bell's conclusion." No, it's not going to be like that. If it's going to be something that really gets us around this, it's going to be something deep. It's going to be something new and a physical principle from which we can see new physics. And so I conclude with a question. Would Einstein have accepted retrocausality as a deep principle worthy of being an axiom? And he might have accepted it just because it was better than anything else. But I'm actually going to conclude with a somewhat stronger demand. I would like to know whether this approach can not only give us a more palatable version of quantum mechanics, but can actually show us something about the world, some experimental result that we didn't know already. Okay, thank you.
Thank you very much. Questions, comments?
I want to elaborate a bit on the comparison that you yourself brought up, namely between special relativity and Lorenz's ether theory on the one hand, and non-locality, non-local quantum mechanics versus retrocausal quantum mechanics. So I see that you can, well, I know you can derive the same quantum mechanics from these different axioms. That's fine. The question is just whether that makes it completely equally believable, the two different formulations, right? If you look at special relativity and Lorenz's ether theory, judged by themselves at the time, you could say, yeah, fine, they're empirically equivalent. You couldn't just, at the time, distinguish by empirical data whether you should adopt one or the other. But special relativity won for different reasons. Looking back, there's even more reasons to prefer special relativity to Lorenz's ether theory, because it's much better embeddable in the rest of physics. And so if you, especially if you, once you know general relativity, Lorenz's ether theory with a preferred state of rest fits much less good than special relativity in the rest of physics. And I wonder whether the same could be said to non-local quantum mechanics versus retrocausal quantum mechanics. Once you know that there's not just non-relativistic quantum mechanics, but also quantum field theory, non-local quantum mechanics fits well with that. How about retrocausal quantum mechanics?
Touché. First of all, special relativity built around itself. It's the context in which it fits so nicely. So, but look, that's why first of all, one can make two demands of increasing severity. The first demand would be, does it let us think more clearly about quantum mechanics, and does it suggest new experiments, for example? And there I think the answer is yes, because I've worked with Aharonov I've had the privilege of working with him for more than 20 years. And his whole approach to, it was very interesting because I never thought about his approach of the two-time formalism as connected so much with non-locality as a possible improvement on, or response to non-locality. But his whole approach of finding weak values and strange new effects comes from this idea which originated in the ABL formalism, the ABL formula, and evolved afterwards into this idea of weak measurements, and that you can find really remarkable quantum effects if you think of the state vector evolving from the future and meeting a state vector evolving to the past. So that's the easier of the two criteria I think we can meet. The harder one, whether we can really discover something that really only works in the retrocausal approach and not in the usual approach, that's an open question, obviously.
Well, thank you for this nice lecture, but I have a worry, though. Of course, in quantum mechanics, there's a distinction between product states and entangled states, and that distinction is clear-cut in the case of pure states. But I understood from your lecture you're trying to apply that to mixed states.
No. I was very explicit, saying that until Jim informs Alice and Bob of the results of his measurements, they can't do anything. They've just got a mixture. There's no entanglement there at all, as far as they can see.
Yes.
Only when they bin their measurements. These measurements apply to the minus, the state with a relative minus. These measurements apply to the state with a relative plus. Then for each bin separately, they can verify that the states are entangled. And that is absolutely necessary, because causality would otherwise be violated if they didn't need that information from Jim.
Yes, but okay, that I might have missed that, but and there was an earlier slide in which you distinguished between a mixture of entangled states and a mixture of product states.
Yeah.
But those mixtures are actually the same quantum state.
Not when they get
not
when they get Jim's results.
When
they get Jim's results, they can verify that if he chose the product state, there's no entanglement.
But then you're applying the projection postulate, and you're conditionalizing on a particular outcome. But before you do that, you just have one particular mixed state, which is actually a multiple of the identity state, which could be interpreted either as a mixture of entangled states or as a mixture of product states. But it's still the same, one and the same quantum mixed states.
Yeah, but
that just shows that the decomposition of mixed states is not unique.
That's if you attribute reality to the mixture as opposed to. I mean, that's completely unjustified, because after all,
that's a mathematical fact.
Yeah, it's a mathematical fact that happens to be irrelevant. I mean, if you look at the Jim's results, otherwise you would say, let them try to verify the GHZ state and its entanglement, and let's kick Jim out of the picture for a while. Then all it has is a mixture. So the GHZ state isn't special at all. It is special. You just threw out 1/3 of the results. That's all.
So this is just a question of clarification. I guess something I missed something in Bell's derivation of his inequalities. There is an assumption that there is something that seems like a retrocausality in his derivation. It's a specific one, and I wondered what is the difference. So if you don't take his assumption, then the derivation is blocked.
Bell
Bell assumes that I mean, you mentioned it, I think, in the context, I mean, you mentioned something about free will, or so Bell assumes that the distribution of the hidden variables at the source is independent of the choice that is made afterwards of what to measure. What is the difference? I didn't get it between this sort of.
That's ruling out retrocausality.
Yes.
Yeah.
So, but if you allow retrocausality, then we already know from. I mean, we know that Bell's derivation of non-locality doesn't go through. So I'm not sure exactly what that means about your.
Bell himself didn't like the idea of retrocausality, and he identified it with fatalism. That's a very interesting question. By the way, I'm relatively recently thinking about retrocausality. That makes me a newcomer, and when I was listening to Yuval Dolev's talk, I was thinking, wow, these are really interesting questions. And once I would have said, these are really interesting questions, but I'm not involved with them professionally. But now I am. And I have this special philosophical training, which is called chutzpah, which, at least around here, which allows me to deal with these issues. But, I mean, one of the problems that I don't know how to deal with yet is the block universe approach, which says that in some sense Alice and Bob have already made their measurements and they have already propagated down back to the preparation of the entangled state. Does that mean that they have free will? I mean, I tried to come up with examples in which you really have no reason to doubt the free will of any of the actors involved. But if you have to say that Alice has already measured, I mean, she doesn't know, there's nobody who can find out what she measured until she measures it. So there's no causal loop, which would be the disaster for any theory. But there's still no assurance that there's still free will in the picture in the block universe. So I mean, maybe this is the sort of question that you're asking.
I don't know if this is a legitimate question. Maybe it's not. I want to understand what exactly retrocausality is about. If I want to think, like I like to think, that the ontology of the theory should not be attached to the state, but only to the events that happens at interactions, then does the very notion of retrocausality remains in some sense or disappears? Because retrocausality is only something that we have to attribute to the state that we want to exist between one quantum event and the other. I don't know if the
I think actually on the contrary, as far as I understand, the PBR theorem tells us that the epistemic approach to quantum mechanics doesn't work.
Oh, no. The PBR theorem, well, maybe I shouldn't tell us that if you believe in hidden variables, then okay. So if you don't believe in epistemic approach, then the full wave equation.
But the only way around the PBR theorem is via retrocausality. So I think that if you want an epistemic approach, then actually retrocausality is what you want.
Okay.
I leave that to you, Yemima.
Okay, that's a good point to thank the speaker again.